Hey, what's up? Christian here with another pfSense and WireGuard video. Today what I wanted to do is spend some time talking about site-to-site VPNs using WireGuard and pfSense. And also I want to talk about some of the potential challenges that you might face when setting up a site-to-site VPN in pfSense. And we're also going to talk about some basic routing and firewall and NAT concepts, which are really important when designing and setting up a site-to-site VPN, irregardless of what protocol you're using, whether you're using WireGuard or OpenVPN. Understanding routing and being able to walk through, a packet as it goes through several different routing tables and decisions are made on where that packet should go. We're kind of going to walk through some of the theory first so that we understand how to, mentally walk through a packet as it goes from point A to point B, which is going to be really important for not only designing setups like this, but also troubleshooting them in the event they don't work. So we're going to kind of cover a lot pretty quickly in this video, but we're going to first start off by talking about some theory, and then we'll go into pfSense and actually look at how that's actually configured. So I'm going to be using, this is just a draw.io topology map here that I've whipped up that kind of demonstrates a very simple setup. We have two sites, Site 1 and Site 2. In my case, I'm using sort of the Comcast LAN that's just broadcast by the Comcast gateway as my simulated WAN. So it's the 10.0.0/24 network. So Site 1 has a WAN interface of .10 and Site 2 has a WAN interface of .11. But we have two sites, Site 1 and Site 2. They each have one LAN, and they have each a connection to a WireGuard tunnel, and that tunnel network is the 10.100.90.0/31 network. Now, maybe you've never seen a /31 network. A /31 network only has two usable addresses. In this case, it's .0, which I've assigned to Site 1, and .1 I've assigned to Site 2. So there's no broadcast, there's no network ID. There's no broadcast because there's only one other client, so there's not really a need for broadcast. This is just a point-to-point link, .0 on one side and .1 on the other. So it's a very, very simple tunnel. It's the best utilization of address space. Two clients, two endpoints, two addresses, that's it. So that's what I'm using for the tunnel network or the transit network for this site-to-site connection. On Site 1, we have a LAN here, and I've just kind of simulated this with some clients. This could be whatever you have on your network. And this LAN is the 192.168.1.0/24 network. And then on Site 2, you might imagine Site 2 as being maybe a co-location in a data center, or maybe it's a remote or branch office. And the LAN here is the 192.168.140.0/24 network. So the 140.0/24 network. And in this case, I just have on my diagram here just a collection of servers, .20, .30, .40, and .50. And what we're going to start off by doing is we're going to kind of simulate, a packet using this little red circle here. And we're kind of going to walk through the various steps and the various routing tables and firewall implications and all the things that are necessary to get a packet from, the LAN on Site 1 over to the LAN on Site 2. And then we'll do the inverse. We'll go from traffic that's initiated from Site 2 to Site 1, which although that's probably never going to happen in this case because Site 2 has servers and Site 1 has clients, and typically the clients are going to be reaching out to the servers, initiating connections from Site 1 to Site 2, not necessarily from Site 2 to Site 1. But again, we're going to kind of walk through all avenues because, again, every environment's a little bit different. You might want bidirectional communication. You might want clients or servers on both sides to be able to freely speak to each other. So we're basically going to walk through, both angles of traffic here, going from Site 1 to Site 2 and Site 2 to Site 1. So let's jump right into that. So we're going to kind of start off by looking at a client over in Site 1. We're going to look at the .120 client, so the .120 client. So this client has an address of 192.168.1.120. Now, basic network theory, if this client wants to speak to any other client on the same broadcast domain, routing is not really involved there. You're going to have an ARP request that's going to translate that IP back into a MAC, and you're going to send Ethernet frames directly between clients on the same broadcast domain. All very standard, simple stuff. However, if a packet is sourced from a client in this LAN that has a destination IP that falls outside of that subnet mask, in this case, or that subnet, the 192.168.1.0/24 network, then that packet is going to be sent to the default gateway of these particular clients. In this case, we can look at just a very truncated routing table. The routing table for these clients is likely to be much more complicated than this, but this is just a very simple routing table for these clients. The default route is via 192.168.1.1/24. So that packet is going to be sent from this client up to the interface on the LAN interface on the pfSense box, in Site 1. Now, again, that decision was largely made by the routing table. The packet's destination was not within the broadcast domain of the client. There wasn't a direct connection to that particular LAN. Like, say, maybe the clients were multi-homed and there was an on-link connection. There was no other routes to that particular subnet, so that packet has to be sent off to a default gateway, and the hope is that the default gateway might know what to do with that packet. So once that packet arrives at Site 1, the pfSense box here at Site 1, again, you're going to have another set of questions that are going to be asked as that packet is evaluated. In this case, we're going to ask, does this pfSense instance have a route to the 192.168.140.0/24 network? And if we look at the routing table as it stands right now, the answer to that question is no. You can see that we have an on-link route to the tunnel network, the 10.100.90.0/31 network. We have an on-link route to the 192.168.1.0/24 network out the LAN interface. But any other traffic is going to be sent to the default gateway, which in this case is the default gateway on the WAN side, or the Comcast side, which is 10.0.0.1. All standard stuff. So as it stands right now, if this client, sourced a packet that was destined for, let's say, the server over here, the .20 server, so 192.168.140.20, that packet, again, is going to be sent to the default gateway on the LAN. And then, again, the routing table is going to be evaluated. There's no route to that particular network, so that packet is going to be in error. Well, it's configured this way, so it's a misconfiguration, but it's not a mistake. It's going to be sent out the WAN and ultimately is going to be dropped because it's a packet that has a destination address that's a private address, which is not routable over the open internet. So that's obviously not what we want. So that's kind of the first challenge, is we have to get this packet going towards Site 2 via the WireGuard tunnel and not out the WAN. That's kind of the first step. Now, there's a couple of things that can happen, though, when that packet leaves. Anytime packet leaves an interface, you have an opportunity to do network address translation. So the question is now, what happens to that packet if we created a static route here? Let's just go ahead and do that. We're going to say that the 192.168.140.0/24 network can be reached via the WireGuard tunnel. And in this case, it's the .1 address, so we'll just say 10.100.90.1. And we'll just put the subnet mask of /31 there. So any traffic that's destined for the 192.168.140.0/24 network is no longer going to be sent out the default gateway, because now we have a route to that network. And that packet is going to be sent towards Site 2 out via the WireGuard tunnel towards the gateway 10.100.90.1, which is Site 2. And again, that's going to work just fine because, again, there's already a on-link route to 10.100.90.0/31 network. So that's going to work just fine. Oops. So as that packet leaves, there's a few things that can happen. The source address can be rewritten to be 10.100.90.0. Or we can choose to not NAT the packet, which is probably what we want to do. And that packet is going to be sent across the tunnel and is going to arrive at Site 2. So let's assume that we're not doing NAT across this tunnel, which we don't need to do because there's private addresses involved and there's no overlapping subnet. So there's no reason to do any kind of fancy business here. Everything should just work if we're not doing NAT. That packet's going to arrive at Site 2. And again, it's still going to be sourced from the 192.168.1.0/24 network, and it's going to be, I have a destination of the 192.168.1.0/24 network. Now, Site 2, the pfSense, again, is going to evaluate the routing table. It's going to say, yes, I do have an on-link route to the 192.168.140.0/24 network, and it's going to happily send that packet down and arrive at the server in question, which is .20. Now, once that packet arrives, we probably are going to have a response that needs to get back to the client. We have a request and we have an answer. We have a question, we have a response. So that response needs to ultimately go back to the client, which is .120. Now, again, the destination and the source addresses are going to be swapped, so it's going to be sourced from the 140.0/24 network on Site 2, and it's going to have a destination address of .1.120 at Site 1. So we have the same problem, where that packet's going to be sent to the default gateway on the LAN of Site 2, and the source address is going to be 192.168.1.120, which, again, if we look at the routing table over in Site 2, we don't have a route. So that's also another challenge. So let's go ahead and add a static route there. We're just going to say 192.168.1.0/24 via 10.100.90.0. So this is going to be the tunnel interface on Site 1, which is, again, 10.100.90.0. And in this case, that is enough to direct that packet back over to Site 1. And again, this packet is sourced from the 140.0/24 network. It has the destination on the 1.0/24 network. Again, the .1.0/24 network is on link, so that it has a route, and it's going to be sent out the LAN interface, and it's going to be sent to the client. And now we have a request to the server, and we have a response from the server. So the first challenge here is we have to think about routes. We have to think about what is that packet going to do every single time there's a routing table involved and a routing decision has to be made. Where is that packet going to go? That is a really, really important concept to understand when you are when you're designing and you're configuring and you're troubleshooting site-to-site VPNs. What is that packet going to do when it is evaluated by each routing table involved? And in this case, there are 4. There's a routing table on the client, there's a routing table on Site 1, there's a routing table on Site 2, and then there's a routing table on the server, again, behind Site 2. So there's 4 routing tables that we have to consider in this particular problem. So let's jump into pfSense and talk about what that looks like. So over here, in the light theme is Site 1, and over in the dark theme is Site 2. These are otherwise identical boxes. Site 1 is actually the 6100 that I was demonstrating in my last video, where I was talking about testing, and I talked about privacy VPNs and remote access. But Site 2 pretty much only has a LAN connection, it has a tunnel, and it has a WAN connection. So Site 2 more or less follows very closely to the situation that we have right here, although Site 1 is actually my edge box. So it has it has some more stuff going on than just, these 3 interfaces. It has VLANs, and it has way more tunnels. It has a tunnel to Mulvad and a tunnel to IVPN. It has a remote access tunnel. So don't let that confuse you. There's just more that's configured on Site 1 that's just not relevant to this diagram and this demonstration. But Site 2 more or less follows the diagram to the letter. So let's go back to pfSense. So on Site 1, let's go ahead and jump into the WireGuard configuration. I've created a new tunnel interface. In this case, it's TUN-WG3, and I've called it Site-to-Site Demo. And if we look at the configuration here, it's very, very simple. I just gave it a description. I gave it a port. In this case, I chose 51825. Again, you can choose any port that you want that just can't overlap with any other ports that are being used on the system, any other UDP ports rather. And I've created a private public key pair. And again, notice that there's no IP addresses configured here because I need to actually assign this interface in pfSense so that I can create a gateway that I can actually use to create static routes to actually direct traffic towards. So that's all you really need to do on the tunnel configuration is create the tunnel, make sure it's enabled, give it a description, give it a port, create a key pair, and hit save. And that's really all you need to do. On site 2, it's exactly the same thing. So we'll go over to VPN WireGuard. And again, site 2 follows the diagram to the T. So we only have one WireGuard tunnel here. It's TUN-WG0. And just for the sake of clarity, both sides of the tunnel are listening on the same port, so 51825. I've generated a key pair. I've given it the same name, and you just click on save, and everything is good to go. Now, under peers, again, this is very, very standard stuff. We have a tunnel that we've assigned the peer to, in this case, TUN-WG0. On site 2, I've given the peer a description of site 1 because this peer is site 1. The endpoint is going to be the WAN address and the port that we picked earlier. Depending upon whether or not these particular peers have a fixed static WAN address, might determine whether or not you want to keep alive. If one of the sides of the tunnel is behind NAT, it's probably a good idea to configure a keep alive. You know, anything that's less than the timeout for your UDP sessions is going to be okay. I just chose 15 here. It works. It doesn't really hurt anything. The keep alive packets are very small, but the goal of the keep alive setting is to keep a UDP path open, punched through any firewalls that might be behind NAT. So if both of your endpoints have fixed addresses and they're directly accessible, either routed over the public internet, or in this case, they're actually on the same WAN segment, the keep alive is not necessary. But just think about that when you're setting up your site-to-site VPN. If one side is behind NAT, then you have a problem where only the side that's behind NAT can initiate communication with the side that has a fixed address. The side with a fixed address can't initiate communication to the side that's behind NAT. So if one side is behind NAT, you would probably want to choose a keep alive of some number that's less than your UDP session length. Okay. The public key here was the public key from the site 1, and the same thing was done here over in site 1. I took the public key from site 2 and configured it over in site 1 under the site 2 peer configuration. So that public key came from site 2, and this public key came from site 1. So this is all standard WireGuard stuff. Now, the allowed IPs. This is going to be an area that we need to spend a little bit of time on, because although we spent some time talking about routing tables over in our diagram, WireGuard actually has its own internal routing table, so to speak, that is used to determine which peer assigned to a tunnel that packet is actually going to be sent towards. Now, WireGuard can be configured in point-to-point. It can be configured in point-to-multipoint. But the rule is you can't have more than one peer assigned to the same tunnel with overlapping allowed IPs. You can't do it. If you try to do that, WireGuard is only going to, I believe it's going to be the last peer in the configuration file is going to sort of win. And that's going to be the peer that is ultimately going to get that allowed IP entry configured, and that's the one that's going to actually get traffic that's destined for that network. So over in site 2, the allowed IPs, we're going to have one entry for the transit network. So we want to allow the 10.100.90.0/31 network to traverse the tunnel. And we also want the 192.168.1.0/24 network. So this, again, is the LAN on site 1. Now, if we go back to site 1, it's exactly the same, except we're now allowing the 192.168.140.0/24 network. So this is really, really important. So basically what this is saying is that if a packet, let's say at site 1, lands here and is sent out the WireGuard tunnel, the choice of which peer to actually send that packet towards, in this case it's just a point-to-point tunnel, is going to be dictated by the allowed IPs. So if this packet has a destination of either, anything on the 10.100.90.0/31 subnet or the 192.168.140.0/24 subnet, that packet is going to be allowed and is going to be sent over to the site 2 peer on the site 2 side of the WireGuard tunnel. That's what allowed IPs mean in the context of WireGuard. You really have to think about it as being there's really two separate routing tables involved. You have the system routing table that we already talked about, and then you have the routing table, the crypto routing table that's used, which is really an association between public keys of peers, and then the subnets that are allowed or accessible via those keys. So crypto key routing is an association between keys and routes. So the decision as to which peer to send that packet towards is going to be dictated by the allowed IPs. So on site 1's side of the tunnel, again, we're allowing the transit network, and we're allowing the LAN on site 2. And on site 2, we're allowing, again, the transit network, and also we're allowing the LAN on site 1. Now, we're not going to talk about dynamic routing. Obviously, if you have lots of different LANs, adding allowed IP entries and adding static routes can get cumbersome and very difficult to manage. So there's better ways of doing that with dynamic routing like OSPF and BGP, which can be ran over WireGuard tunnels with some caveats, particularly around multicast traffic, because WireGuard tunnels can't pass multicast traffic, only unicast traffic. That's a topic for another video on using, free range routing, FRR and OSPF and that sort of thing to do dynamic routing between two sites. But in this case, it's just very, very simple. We're only going to allow the transit network and then each corresponding LAN from each side of the link. So that is the WireGuard configuration. And we'll go ahead and just hit save. It shouldn't require me to restart anything because nothing actually changed. Now, if we go to status and we go to the peer status for our tunnels in question, you can see that we have the peer on site 2, which is the peer on site 2 is site 1. We're handshaking. We have our allowed IPs. And again, you can see that I've done quite a bit of testing here. I've passed quite a bit of traffic between site 1 and site 2. And again, it's going to look exactly the same, just in reverse on site 1. We have a site 2 peer. And in this case, I was actually sending quite a bit of traffic from site 2 to site 1, which is why the transmit here is 38 gig and the receive is 38 gig on site 1. Okay, so that's the WireGuard side of the configuration. Now, we still have to think about the system routing table and what's going to actually happen with those packets. Now, we have to assign the WireGuard tunnels to pfSense interfaces because we ultimately are going to have to create gateway entries to create static routes. Because again, we're using static routing in this particular video. We'll talk about dynamic routing in a future video. But because we actually need to send traffic towards a peer on a WireGuard tunnel, we need to assign it in pfSense so that we can use that built-in pfSense tooling for creating gateways and creating static routes. Otherwise, if you don't go through this process of assigning the interface to pfSense, pfSense is not really aware that that interface actually exists. So this is the way that you tell pfSense, yes, this interface exists, and then it allows you to create gateways and create firewall rules and NAT rules that are specific to that particular interface. So again, I'm just going to give this a name. In this case, it's just site-to-site demo, static IP. I'm clamping the MSS at 1380, an MTU of 1420, probably because my transit network is going to be 1500 and the overhead, the worst case scenario overhead for a WireGuard packet is going to be 80 bytes. If you're talking about IPv6. If you know that you're only doing IPv4 traffic, you can actually bump the MTU up to 1440. But if you set it at 1420, you'll have no problems with either IPv4 or IPv6. So 1420, this is one of the reasons why when you create a WireGuard tunnel, the WireGuard tools creates, or ifconfig or ifconfig or whatever you're using to create the tunnel, it's going to create it with a default MTU of 1420. So that's kind of the logic behind that. But pfSense, again, doesn't really know that this interface is a WireGuard tunnel. So if you leave that blank, it's just going to use a default MTU of 1500, which is going to cause fragmentation and whatnot. So go ahead and set that to 1420. It'll help in the long run. Again, we don't want to block private networks because this is a private transit, and we can just leave everything else blank, and we can click save and apply. And I'll let that apply. Okay. And again, the same thing over in Site 2. I have assigned the TUN-WG0 interface to an opt interface. And again, it's exactly the same, but this side is 10.100.90.1/31, and everything else is exactly the same. Now, you might have noticed that I have not chosen an upstream gateway, even though if I click this drop-down box, you can actually see that there is a gateway that falls on that subnet. And there's a good reason why I have not done this. When you actually select an upstream gateway on the interface configuration in pfSense, what actually happens is this is one of the pieces of information that pfSense uses when it's determining which interfaces to create automatic outbound NAT rules. And we don't want to do NAT over the tunnel. Now, if you actually chose an upstream gateway for both ends of the link, traffic will still work. The packets will still flow. Everything will still work as it should. However, what's going to end up happening is that all of the traffic that's sourced, let me go back to the diagram here, that's sourced from the 1.0/24 network on site 1 going to site 2 is going to appear as coming from the .0 interface on the transit network, which is probably not your goal, okay? So just leave the upstream gateway empty on both sides of the link, and that will ensure that an automatic rule is not created that's going to NAT that traffic as it leaves the site-to-site interface towards that gateway. You don't necessarily, it's probably not what you want. So that's one thing to kind of stay on the lookout for. If you set up an upstream gateway, that's what pfSense uses when it's determining which interfaces and the source addresses and whatnot to actually create automatic outbound NAT rules. So if you leave that blank, then it's completely on you as the administrator to create the static routes and make sure that everything else is copacetic with the firewall rules and that sort of thing to make it work. And again, you probably want the servers to still be aware of, the source address from the clients and vice versa. So just make that aware. Make sure that you're aware of that. If you configure an upstream gateway, it's probably not going to be the behavior that you want, at least in this particular case. So that's one thing to look out for. All right, so then the next thing that we're going to do is we're going to look at our gateway configuration. So we're going to go ahead and let this apply. We're going to go to System and Routing. Again, this is on Site 1. And all I've done is I've created a Site 2 gateway. I've called it Site 2 GW4 for V4. And the gateway address is 10.100.90.1 because we're on Site 1. We want the Site 2 side of the link, which is 90.1. It's also probably important to make sure that your default gateway, is not set to automatic. That can cause some weird behavior. So if, either choose your default gateway or, if you have multiple multi-WAN scenario, create a gateway group and set the gateway group as the default gateway, but don't leave it as automatic. This is a piece of advice that, was advertised, long before the WireGuard package was a thing. Even when WireGuard was actually built into pfSense, that was the recommendation, to leave the default gateway fixed and not as automatic. So that's what I've done there. And then once you create the gateway, then you can create a static route. In this case, I'm telling Site 1 that instead of sending traffic that's destined for the 140.0/24 network, so the LAN on Site 2, instead of sending that traffic out the default gateway and towards Comcast, we want to send that traffic towards Site 2's side of the tunnel. In this case, 10.100.90.1. And if we go to the routing table, again, we can see that if we find 192.168.140.0/24, you can see that we have a route for that particular network at that particular gateway, and it's out in this case, TUN WG3, which is the WireGuard tunnel on Site 1. Okay, so again, the same thing is configured on Site 2. We have a gateway for Site 1, which is Site 1's gateway interface, or Site 1's WireGuard interface, so the Site 1 side of the WireGuard tunnel. And again, we have a static route saying that the LAN on Site 1 can be reached via the tunnel on Site 1, on the Site 1 side of the WireGuard tunnel, the 10.100.90.0 IP. Okay, so that is the static routes. And just to kind of show you that, if we go to Diagnostics and Routes, on site 2, you can see that we have a route to the 1.0/24 network via the gateway 10.100.90.0 out the TUN-WG0 interface, which is the site 2 side of the WireGuard site-to-site tunnel. All right, and then finally, we need to talk about firewall rules. So we're going to go ahead and look at the firewall rules on site 1 first. So we'll click on firewall, we'll go to rules, and let's go ahead and look at the WAN side of each particular site. So under WAN, we need to allow the WireGuard ports, UDP. In this case, I have a port alias that just has a list of all of the WireGuard ports that I'm currently using on this particular pfSense box, and I'm just allowing IPv4 UDP to allow the WireGuard ingress at site 1, and then I'm doing the exact same thing on site 2 for, again, UDP allowing any of the WireGuard ports that I have open up on site 2 via the WAN. So that's really important to allow the WireGuard the side of each, the WireGuard peer on each side to actually to send traffic to the other side of the WireGuard tunnel. The next thing we need to look at is the actual transit network itself. Now, I have mine left wide open, but you can actually restrict that as much as you need. But again, just remember that you do have firewall rules that are dictating traffic that's actually flowing across the actual WireGuard tunnel itself. So if you are having an issue with traffic, make sure that your firewall rules make sense there. Now, to make sure that this is working correctly, you might want to also consider the fact that there's a difference between the WireGuard interface group and individual interfaces. So this is kind of basic pfSense theory, but interface groups are evaluated first before individual interface rule sets. So in this case, what I recommend doing is actually changing the behavior of the interface group membership. The default is to actually include all WireGuard tunnels, whether they're assigned or unassigned, to include all of those in the interface group. In this case, what I've done is I've told WireGuard to only add unassigned tunnels to that WireGuard interface group. So go to WireGuard settings, interface group membership, and choose only unassigned tunnels. And what that will do is it will ensure that the WireGuard interface group has no impact on your assigned WireGuard tunnels. So in this case, the only rules that are going to apply for the actual site-to-site tunnel are going to be, in this case, the site-to-site demo interface that I assigned on both site 1 and site 2. And again, if you look at site 2, I have the exact same thing configured: only unassigned tunnels for the interface group membership on site 1 and site 2. So we've already configured our WAN firewall rules to allow WireGuard ingress traffic. If you've got if one of the sides of your site-to-site tunnel is behind NAT, then there's really no need to open up any rules on the WAN. It just means that that particular peer is going to have to initiate traffic and open up that UDP, punch that hole through the firewall, that UDP path, and then that will allow site 1 to then come back through that path, and then you can use keep alives to keep that path open so that both sides can communicate without requiring the side that's dynamic to initiate a connection each time. Otherwise, you only have, the communication can only be initiated from one side if the tunnel is not currently active. Remember, WireGuard is stateless. It's only, it just sends packet towards an endpoint. And if that UDP path, if there's not a path, from one peer to the other, and that path can't be established, then it's not going to work. So again, it's just something to think about with keep alives and whether or not you have a site that's behind NAT or not. And then finally, we're going to look at the rules for the LAN. Again, this is just a demonstration, so I just I like to just keep things wide open. Allow things get things working, and then start to dial in the firewall rules. In this case, the LAN on site 1 is actually a VLAN. a little confusing. Again, the site 1 instance is actually my edge, so there's way more going on here than what is in the diagram. But again, I'm just allowing all traffic. And then on site 2's LAN, which is actually, again, following the diagram to the letter, I just have an allow all rule there as well. So that's pretty much the firewall rules that are required for making this work. Now, to actually demonstrate this, I'm going to go ahead and go back to the dashboard on both sides, and we're going to actually look at what address I'm actually coming from. So if you notice on site 1, I am actually coming from the client. The client that I'm using, my notebook here, has an address of 192.168.1.109. So that's the address that I'm connecting to site 1 via. Now, if you go to site 2, you'll notice that address is exactly the same, even though site 2 has no awareness besides that static route of the 192.168.1.0/24 network that's on site 1. Now, let me go ahead and switch over my LAN connection. I'm going to switch my LAN connection from site 1 to site 2. And we'll let that reestablish. So I'm pulling an IP. So now I should have an IP on the 192.168.140.0/24 network. So if I refresh site 2, you can see that my IP address has changed. It's now 192.168.140.100. And in fact, if I go to status in DHCP leases, you can see that, yes, this is my laptop here, and it has an address of 192.168.140.100. And if we go back over to site 1 and I refresh, you can see that, yes, this connection is being sourced from 192.168.140.100. So it works in both directions. So if I go back, let me just swap back over to site 1. And we'll let that establish and pull an IP. And if I refresh this, you can see that now my address is 1.109. And if I go back to site 2, again, my address is 192.168.1.109. Now, I would like to demonstrate the behavior if you are accidentally doing NAT over this connection, which is something that might actually end up happening, and it might be a source of confusion in trying to understand what's going on. So what I'm going to do is I'm going to go back to interfaces, and I'm going to go to assignments. I'm going to go to site-to-site demo, and I'm actually going to choose an upstream gateway on both sides. So go back to site 2, and we're going to do the same thing. Okay, and we'll click apply. Let that do its thing. Okay. Now notice that I still have connectivity, not a problem. Okay. And there's still states involved here, so I'm probably going to need to flush some states. Anytime you make changes with NAT, there's always a chance that you've got a state that's alive that's going to cause some hiccups here. But notice that when I go to the when I go to outbound NAT, you can see that now the site-to-site demo interface now has those automatic NAT rules, and you can see if you look closely at the addresses that on site 1 we're natting 192.168.140.0/24. So we're gonna have NAT involved, leaving this interface. So we're gonna reset the states, and we'll notice something peculiar about the source address that's actually shown here in pfSense as to what the IP address is that the traffic is coming from. So let's just go back here, and I'm just going to go ahead and reset the state table. Actually, I want to reset the state table on site 2 first. Otherwise, I'm going to have to wait for site 1 to come back alive. So I'm going to do that, reset the state table there. And we'll just let this sit for a second as the state table is flushed and connections are reestablished. Again, this is typical. When you reset the state table, it can appear as though the browser session has hung. You just might have to refresh a little bit here, but it will eventually come back to once it figures out what's going on. Right. So notice that I'm still looking at the 192.168.1.109 when I'm on site 1. But if I go to site 2, notice that it looks like I'm coming from 10.100.90.0. Now, that is the scenario that I was talking about here, where if we choose that upstream gateway on both sides of the link, then the NAT is involved if you have automatic outbound NAT rules being created, and that packet is being NATed as it leaves the WireGuard interface towards site 2, and it's actually having its source address rewritten to be 10.100.90.0. So the same thing is true in reverse. So let me go ahead and switch back to site 2. And we'll let that reestablish a connection. Okay, looks like I've got an IP. So when I refresh site 2, again, I'm local to site 2. So my address should be 192.168.140.100, which it is. But when I go to site 1, this address is going to be different. It's going to be 10.100.90.1. If I refresh, you can see that now it's looking like it's behind NAT. Now this can be troubling if you're trying to, get really precise about your firewall rules and your ACLs, or maybe your servers for some logging purposes. You need to, log the actual source address of every single connection on one side or the other. And if you're doing NAT, then obviously that information is going to get lost, because all the traffic that's coming from site 1 is going to appear as though it's being sourced from the site 1 side of the tunnel. And the inverse is true. Any traffic being sourced from site 2 towards site 1 is going to appear as though it's being sourced from 10.100.90.1, which again is probably not the behavior that you want. So that's one of the reasons why I was not choosing an upstream gateway on both sides of the tunnel. So if I undo that and choose none and apply, and then again we can go back to firewall NAT outbound. You can see that no longer is the site-to-site demo interface being included under automatic rules. That's also going to be true under site 2. And I'm probably not going to see that change immediately because there's still active states in the state table. But if I flushed the states, then that would obviously go back to actually reflecting the actual original address and not being hidden behind, not being natted and hidden behind the transit IP address. So that's just something to look out for when setting up site-to-site VPNs. Now you can do other things too. You can do port forwarding. You can think of outbound NAT as obviously translating traffic as it leaves an interface. Well, port forwarding allows you to match and manipulate traffic as it enters an interface. So that might be a particular case, like let's say that you were keeping everything behind NAT and you needed to do some port forwarding to some internal servers or whatnot. You can totally do port forwarding here as well. You would just go to port forward, add, and choose the site-to-site demo interface, and then you can do your traffic matching and doing your rewrites and whatnot there as well. So port forwarding also works. I just don't have a use for that here in this demonstration, but you can do it. So hopefully this gives you some tips and tricks and some troubleshooting steps that you can use when designing site-to-site, experimenting with site-to-site and WireGuard. It's pretty straightforward, but it can, you can find yourself bashing your head against the wall, and it probably is going to be something pretty simple. Thankfully the WireGuard protocol is so simple that at least from the WireGuard side of things, everything is pretty cut and dry. Understanding allowed IPs and crypto routing, there's a little bit of a learning curve there, but it's really not that bad. But really, when it comes down to effective site-to-site configurations, it really comes down to a basic understanding of routing, firewall rules, static routes, dynamic routes. You can even do policy-based routing if you wanted to take that approach. There's several different ways that you can make this work. But this is just the way that I do it here. So if you have any questions, make sure to leave them in the comments below. If you haven't already, make sure to subscribe and click the like button and the bell icon so you don't miss any future content. This channel is all about pfSense, WireGuard, and networking. So if that's what you like, make sure to subscribe so you don't miss any future videos. And again, if you feel like I've made a mistake or I've missed something, let us know in the comments below and we'll keep the conversation going. So thanks for watching and we'll see you next time. Thanks.